Let me take you back to that moment when everything flipped upside down. We're out there hunting near-Earth objects, the usual suspects, rocks that could potentially smash into the planet and ruin everybody's day. And then boom, one night the data comes in and it's like the universe just dropped a bomb on us. The very first orbit solution hit us like a freight train. This thing wasn't just on some wild elliptical path around the sun. No, no, no. It was hyperbolic, bro. Moving so damn fast it couldn't possibly be stuck in our solar system's gravity well. It came screaming in from interstellar space, took a hard turn around the sun, and was already hauling ass back out into the deep black. First confirmed interstellar object ever. We were like kids on Christmas morning who just found out Santa's real and he's an alien. We ended up naming it one Oumuamua Hawaiian for Scout from the Distant Past or Messenger that reaches out first, something badass like that. The excitement was off the charts, man. Astronomers had been saying for decades, yeah, statistically there's gotta be tons of these things flying through our system all the time, but we'd never actually caught one. And now here it is, this cosmic hitchhiker just cruising through the neighborhood. Then the weirdness started piling up fast. First thing that made us go, what the hell, was the light curve. Every time this thing spun, its brightness was changing by a factor of 10, sometimes more. 10! For reference, your average asteroid might flicker a little, maybe 2 or 3 times brighter at most. This was like watching a lighthouse on steroids. That told us immediately the shape had to be insane, like 5-to-1, maybe even 1-0-to-1 length to width. Picture a giant cosmic cigar or a pancake the size of a city block flipping end over end. Nothing in our solar system looks like that. Our rocks are all potato-shaped and lumpy. This thing was a needle in space, bro. And the way it was tumbling? Holy crap. It wasn't doing a nice clean spin like a rifle bullet. It was in full-on non-principal axis rotation like if you threw a football with a wicked spiral and it's also flipping end over end at the same time. That kind of chaotic tumbling usually means something got absolutely hammered in a collision, but this thing had been cruising through empty space for maybe hundreds of millions of years. What the hell hit it out there? We were scrambling, man. Every big telescope on Earth, Hubble, Gemini, VLT, we were begging, borrowing, and stealing time to suck every photon we could out of this thing before it disappeared forever. Clock was ticking hard, it was already fading fast. At first we thought asteroid. No coma, no tail, no nothing, just a dark reddish rock. Super low albedo, like it had been baked by cosmic rays forever. Cool, weird shape, interstellar origin, but still natural. We could wrap our heads around that. Then the orbit got refined with more data, and that's when the room went dead silent. There was this tiny little extra acceleration as it was leaving the solar system. Not huge, but real. Way outside the error bars. It wasn't following pure gravity anymore. Something was pushing it gently, but consistently away from the sunday. Classic non-gravitational acceleration. Now, normally when you see that with a comet, you go, oh, outgassing, rocket effect, no big deal. Ice heats up, turns to gas, shoots out one side, boom, you get thrust. Happens all the time. Problem was, we saw zero evidence of any outgassing, no coma, no tail, no dust, no gas signatures, nothing. We looked with the best instruments humanity's ever built, and it was clean as a whistle. So you've got thrust, but no visible propellant. It's like watching a car accelerate down the highway with no engine noise, no exhaust, no fuel, just smooth, silent push. What the hell is triggering it, Jamie? We tried everything to keep it natural. Water ice? Nope, would have made a huge dusty coma we would have seen from a mile away. CO? CO2? Those supervolatiles could maybe work at greater distances, but even they drag dust with them, and we saw zero dust. The limits we put on dust were insane, like thousands of times lower than any normal comet. And because it's tumbling like a maniac, any normal jet coming off one spot would have torqued the hell out of the rotation rate. We'd have seen the spin speed change over weeks. It didn't. Whatever was pushing, it had to be perfectly balanced across this giant, weirdly shaped, chaotically spinning object. The odds of that happening naturally with regular outgassing? Bro, it's like winning the lottery while getting struck by lightning on your birthday. That's when the whole thing went from cool interstellar rock to straight-up mystery that keeps you up at night. We had a dark, elongated, tumbling interstellar object showing thrust with no visible mechanism. And that, my friends, is when the real conversation started. I remember one of my colleagues joking that the only way to explain it was if the object was a perfectly engineered, self-correcting thruster system. The joke was a nervous release, a way to acknowledge the sheer difficulty of the problem without resorting to the extraordinary. But the extraordinary was precisely what the data seemed to be pointing toward. The scientific community, however, is rightly conservative. Extraordinary claims require extraordinary evidence, and the evidence we had a tiny, faint deviation in an orbital path was not enough to overturn centuries of established physics and jump to the conclusion of alien technology. We had to exhaust every possible natural explanation, no matter how exotic or unlikely. The search for a natural answer became a race against time, a desperate attempt to fit a square peg into a round hole, or perhaps a cigar-shaped peg into a potato-shaped hole. This led us down a path of increasingly speculative, yet still purely physical, hypotheses. We started to consider materials that don't exist in abundance in our solar system but might be common in the cold, dark reaches of the interstellar medium. We began to look for the invisible propellant, the ghost gas that could push a cosmic needle without leaving a trace. One of the most compelling, and most recent, natural explanations proposed that Oumuamua was a fragment of solid nitrogen ice, or perhaps solid hydrogen ice. Let's start with the solid hydrogen idea. Hydrogen is the most abundant element in the universe. In the extremely cold environment of a giant molecular cloud, hydrogen gas could theoretically condense into solid H2 ice. This ice is incredibly volatile, sublimating at temperatures far lower than water or even CO. If Oumuamua were a chunk of solid hydrogen, it would explain the lack of a visible coma. As the H2 ice sublimated, the resulting hydrogen gas would be nearly invisible, and because the ice is so fragile, it would likely not drag any dust with it. The sublimation would be so rapid and complete that the object would simply vanish as it passed the sun, leaving no residue. The problem with the solid hydrogen hypothesis, however, is its fragility. Could a chunk of solid hydrogen ice survive the journey from its home star across the vast, radiation-filled expanse of interstellar space and then survive the close approach to our sun? The answer, according to many models, is a resounding no. Cosmic rays and stellar radiation would have rapidly eroded the H2 ice, causing it to sublimate away long before it ever reached our solar system. The sheer amount of H2 ice required to survive the journey and still produce the observed acceleration upon reaching the sun seemed to violate the laws of cosmic endurance. It was a beautiful, elegant solution, but one that seemed to crumble under the weight of astrophysical reality. This brought us to the solid nitrogen ice hypothesis. This idea suggests that Oumuamua was a fragment of a Pluto-like exoplanet, a body composed largely of frozen nitrogen, which was violently ejected from its system. Nitrogen ice, or N2 ice, is less volatile than solid hydrogen but more volatile than water ice. The key insight here is that N2 ice, when sublimating, could produce the required thrust without generating a detectable dust coma. Furthermore, the rate of sublimation could be tuned to match the observed non-gravitational acceleration. The N2 ice model also offered an explanation for the object's extreme shape. If Oumuamua was a piece of a larger, tidally disrupted body, the process of ejection and subsequent erosion by interstellar radiation would preferentially strip away the outer layers, leaving behind a highly elongated, flattened remnant. The erosion would also explain the object's relatively small size. The N2 ice model is currently one of the strongest contenders for a natural explanation. It addresses the non-gravitational acceleration, the lack of a coma, and the unusual shape. It is a testament to the ingenuity of planetary science, forcing us to consider compositions that are rare in our inner solar system but might be common in the outer reaches of other systems. It is a complex, multi-layered hypothesis that requires us to accept a chain of unlikely events: the formation of an exo-Pluto, its tidal disruption, the ejection of a pure N2 fragment, and its survival across interstellar space, but it remains within the boundaries of known physics. However, even the N2 ice model has its detractors and its own set of lingering questions. The biggest issue is the albedo, or reflectivity, of the object. Oumuamua was observed to be quite dark, reflecting only about 10% of the light that hit it. Nitrogen ice, particularly fresh nitrogen ice, is highly reflective. For the N2 ice model to work, the object's surface would have to be covered in a thick layer of dark, organic-rich material, a kind of cosmic tar, which would have accumulated during its long interstellar journey. This is plausible, but it adds another layer of complexity to the explanation. Furthermore, the sheer number of such objects required to explain the detection of Oumuamua, given its short observation window, suggests that the galaxy must be teeming with these ejected exo-Pluto fragments, a population that is not entirely consistent with current models of planetary system formation. The debate is fierce, and it highlights the fundamental challenge of studying an object that we only saw for a few weeks, an object that is now too faint and too distant to ever observe again. We are left with a handful of data points and a mountain of speculation. This brings me back to the question that captivated the public imagination and frankly captivated a part of my own. What's triggering it? When a phenomenon defies all the most common and elegant natural explanations, the mind naturally drifts to the possibility of the artificial. I must be clear. The vast majority of the scientific community remains firmly committed to a natural explanation. That is the bedrock of our discipline. But there is a small, vocal minority, led by highly respected figures, who have dared to suggest that the simplest explanation for the observed anomalies is that Oumuamua is not a rock, not a comet, but a piece of technology. The argument for the artificial hypothesis rests on the cumulative weight of the anomalies. It's not just one strange thing, it's the combination of three: the extreme elongation, the non-gravitational acceleration, and the lack of a visible coma. Consider the shape. Why would a natural object be so much longer than it is wide? While tidal disruption can create elongated fragments, the required aspect ratio of 10:1 is at the very edge of what is physically plausible for a natural body. But for a piece of technology, an elongated shape is highly functional. A long, thin structure is more resistant to structural failure under stress, and it maximizes the surface area for a given volume, which is crucial for a light sail. This is where the most provocative idea comes in. The non-gravitational acceleration, the tiny, persistent push away from the sun, could be explained by the pressure of solar radiation acting on a very large, very thin object. A light sail is a proposed method of interstellar travel, a massive, thin sheet designed to be propelled by the momentum of photons from a star. For the observed acceleration to be caused by solar radiation pressure, Oumuamua would have to be incredibly thin, perhaps less than a millimeter thick, with a density far lower than any known natural rock or ice. This low density, coupled with the large surface area, would allow the subtle force of sunlight to create the observed thrust. If Oumuamua was a light sail, it would explain everything. The extreme elongation a sail is a sheet, which is extremely thin and wide, the non-gravitational acceleration, it's being pushed by light, and the lack of a coma, it's not outgassing, it's a solid structure. The tumbling motion could be explained as the result of damage, or perhaps a deliberate maneuver, a sign that the object is derelict, a piece of space junk from an advanced civilization, a cosmic buoy that has been drifting for millennia. The implications of this hypothesis are staggering. If it were true, it would mean that we have detected the first evidence of extraterrestrial technology, a piece of hardware from another star system. It would mean that the question, what's triggering it, has a simple yet profound answer: intelligence. But the scientific method demands that we remain skeptical. The artificial hypothesis is a hypothesis of last resort, one that we only entertain when all natural explanations have been exhausted. And as I've detailed, the natural explanations, particularly the N2 ice model, are still being refined and debated. The problem is that we can no longer collect data to definitively prove or disprove either side. Oumuamua is gone. We are left to argue over the interpretation of a few weeks' worth of light curves and orbital deviations. The object's journey began long ago, in a star system we can only guess at. It was ejected, perhaps by a gravitational slingshot from a giant planet, and began its lonely voyage across the interstellar void. For millions of years, it was exposed to the harsh environment of space, bombarded by cosmic rays, slowly accumulating a layer of dark, organic material. It entered our solar system from the direction of the constellation Lyra, moving at a speed that suggested it was not a recent ejection but a long-term traveler, a true denizen of the galactic plane. Its trajectory, by the way, was not just fast, it was ridiculously fast. I mean, 26 kilometers per second relative to the sun? That's enough to get you from New York to Los Angeles in under a minute, if you could even survive the trip. And it wasn't just a straight shot, the path was hyperbolic, like it wasn't tethered to our sun at all. It came in, it swung around, and it was gone, back to the interstellar void from which it emerged. And that's what makes this thing so damn fascinating. It's not just a visitor. It's a messenger from another star system, carrying secrets about who knows what out there. And we're just standing here trying to make sense of its weird physics. And speaking of weird physics, the shape, oh man, the shape. When astronomers tried to model it, the numbers got crazy. It's not a regular rock, not a standard cigar-shaped comet, nothing like anything we've seen. Estimates suggested it was incredibly elongated, maybe 10 times as long as it is wide. That's insane. Most objects in space are more like spheres or potato shapes, right? But this thing is basically a cosmic licorice stick tumbling through the void. And it's spinning chaotically. Like, not just a steady spin, but this weird tumbling, unpredictable rotation. You try to simulate that in a lab, and the equations go nuts. A long, thin, tumbling object moving the way it does? That's a nightmare for astrophysicists. Now, Let's go back to that non-gravitational acceleration, because that's where things get really bizarre. Imagine you're trying to explain how something moves faster than gravity alone can account for. Normally, in our solar system, comets do this all the time. They outgas, jets of gas shoot out, and boom, tiny propulsion system, all natural. But here's the kicker. Oumuamua doesn't have a visible coma. No ice cloud, no dusty tail, nothing. And yet, the acceleration matches the predictions for a comet-like push perfectly. It's the universe sending us mixed signals. Look, here's the data, but don't expect it to make sense. It's almost taunting. Man, the acceleration is proportional to 1 over the distance squared classic solar influence, and yet the mechanism is invisible. You'd think if it's outgassing, we'd see it. But nope, nothing. And that brings us to the radiation pressure hypothesis, which is just as wild. Some scientists proposed, what if this thing is ultra-thin, like a light sail, something so thin that sunlight itself could push it along? That's the sort of stuff you'd design in a sci-fi lab, not stumble across in space. But the physics works. The numbers line up. A sheet-like structure could, in theory, get pushed by photons enough to account for the acceleration. And if you start thinking about the origins of such an object, well, it opens up doors to possibilities we haven't even dared to consider seriously before. Alien tech? Maybe. Natural phenomena we've never observed? Could be. That's the beauty and terror of it. It challenges everything we assume about what's out there. Then there's the rotation and tumbling issue. If Oumuamua were outgassing chaotically, the spin should be all over the place. Imagine jets firing off randomly from different sides. That's going to make the spin chaotic, unpredictable, and probably violent. But when scientists analyzed the light curve, basically how the brightness changes as it spins, they saw a smooth pattern in the acceleration. Almost too smooth. Elegant, even. It's like nature said, I'll give you thrust, but I'll do it in a controlled, precise way. That's not what we expect from a haphazard chunk of ice cracking under thermal stress. That smoothness, it's what keeps people up at night, scratching their heads. And think about the composition. Let's say it's ice, sure. N2 ice, CO, CO2, something super volatile that could survive interstellar travel. That's plausible. Maybe it's been drifting through space for millions of years, frozen solid, until it got close enough to a star to wake up. But the ice would have to survive intense cosmic radiation, collisions with dust particles, micrometeorites, and still remain intact enough to produce this precise acceleration. That's not impossible, but it's unlikely. And if it's not ice, then what? Metal? Rock? Some hybrid, weirdly porous structure that responds to sunlight? The possibilities get stranger the more you think about it. And here's where the story goes full-on mindbender. The spin tumbling, the hyperbolic path, the smooth acceleration without a visible coma, put it all together, and you have an object that's almost designed, almost engineered. Now, don't get me wrong. I'm not saying little green men piloted it in a cosmic spaceship. That's not science. But when natural explanations struggle to fully account for the observations, you're forced to broaden your thinking. You start considering scenarios that would have been dismissed a decade ago. You start asking, what kind of natural processes could produce something so alien in appearance, motion, and behavior? And let's not forget the observational constraints. We only got a short window to see this thing, a few weeks, maybe months. It's moving insanely fast, and by the time we spotted it, it was already retreating back into interstellar space. That's frustrating as hell for scientists. They're trying to measure brightness variations, spin states, trajectory, acceleration, all while the object is fleeing. So any conclusions we draw have to be made with partial information, which is always tricky. It's like trying to understand a movie by watching 5 minutes of the trailer. Now, zoom out a bit. What does this mean for our understanding of the universe? For starters, it tells us interstellar objects are real, and they're visiting our solar system more frequently than we thought. Oumuamua is the first we've observed, but statistically, it's probably not alone. Every year, maybe dozens of these things are zipping through, mostly too small or too faint to detect. And each one is a messenger from another star system, carrying clues about the chemistry, physics, and history of far-off worlds. It's humbling and thrilling at the same time, like the cosmos just handed us a postcard and said, "Here, take a look." And think about the cultural impact. Suddenly, there's this object that captures the imagination of not just astronomers, but the public, the media, even science fiction enthusiasts. It's fast, it's weird, it's mysterious, and it defies easy classification. And everyone has a theory. Comet, asteroid, alien probe, natural ultra-thin ice sheet, the debate rages on. That's the beauty of it. Science thrives on uncertainty, on the things that make you scratch your head and say, wait, What and Oumuamua is pure unfiltered cosmic mystery. Then there's the follow-up. After Oumuamua passed, astronomers started thinking, how do we detect the next one earlier? How do we prepare? Because if something comes through, we want to know as much as possible. That's why surveys like Pan-STARRS exist, to scan the sky continuously, to catch these fleeting visitors before they vanish. And each detection is a chance to test our understanding of physics, dynamics, and the behavior of materials in extreme environments. Oumuamua was like the first call, the wake-up signal. Pay attention. The universe is sending weird stuff your way. And yeah, it's crazy, man, because it challenges the assumption that the solar system is isolated, that we understand the population of objects here. Every comet or asteroid we've studied before was born in our solar system. We know their chemistry, their dynamics, their shapes. But Oumuamua, that's a whole new category. It's a reminder that the galaxy is full of surprises, that our corner of space is just a tiny window into a much larger, stranger reality. It's both exhilarating and a little unsettling. And let's circle back one last time to the acceleration. The fact that it scales with the inverse square of the distance to the sun, that's really the smoking gun. It says there's a force acting in a way that's predictable, consistent, and tied to solar energy. No other natural force we know of fits that pattern at this scale. Gravity alone? Nope. Chaotic outgassing? Doesn't match. Radiation pressure on a thin structure? Plausible. And that's why discussions about ultra-thin, natural, or artificial objects aren't just idle speculation, they're grounded in physics. The numbers don't lie. The universe is handing us clues, and we have to follow them wherever they lead. So yeah, when you step back and look at the full picture, the speed, the shape, the trajectory, the tumbling, the smooth yet unexplained acceleration, it's like staring at a cosmic puzzle with pieces that don't quite fit. And that's the beauty of it. Science isn't about having all the answers. It's about chasing the questions, following the weirdness, and trying to make sense of it, even when it seems impossible. Oumuamua isn't just an object, it's a challenge, a reminder that the universe is weirder, more complex, and more awe-inspiring than we often give it credit for. It's the kind of thing that keeps you up at night, staring at the sky, thinking, what the hell else is out there? And maybe that's the most important part. The fact that we don't have a neat, tidy explanation doesn't mean we've failed. It means we've been given a glimpse of something larger, something that pushes the boundaries of our understanding. It's rare, it's humbling, it's exhilarating, and it's why we keep looking up, keep building better telescopes, keep asking the impossible questions. Because one day, the next interstellar visitor might reveal even more, might challenge everything we think we know, and remind us that in the vastness of space, there's always room for awe. Oumuamua came, it dazzled, it confused, and it left. But in its wake, it left questions that will fuel curiosity for generations. And that, man, is pure magic. And then there's the spin-up problem. This is huge. Normally, when a comet outgasses, the jets of gas act like tiny rocket engines, spinning the object faster. That's been observed over and over again. But here's the thing. For Oumuamua, the observed acceleration should have caused a significant spin-up. Yet, when scientists analyzed the light curve, which is basically how the brightness changes as it tumbles, they didn't see the expected spin change. None of it. That's a subtle detail, but it's a big deal. The force is there, clearly, but the rotational effect is absent, and that, dude, is nuts. Because it implies that whatever is causing the push is either perfectly centered on the center of mass, like it's the universe's perfect little setup, or it's a force evenly distributed across the surface. And that's exactly how solar radiation pressure would work on a thin, flat object. It's eerie. So now you have this perfect storm of anomalies. You've got a push, but no visible gas. You've got a push, but no spin change. You've got a crazy elongated shape, they're talking 10-to-1 ratio, and no natural way to form it. Each of these things on its own is weird but maybe explainable. But all three together? That's when your brain just starts melting. Natural explanations start hitting a wall. And scientists, man, they love hitting walls like this because it's where the fun begins. I've gone through so many papers on this thing, it's ridiculous. Every single one is trying to patch the holes with some exotic theory. One paper says, oh, maybe it's a fractal dust aggregate, like some cosmic fluff ball that's so low in density the sunlight can push it. Another says, no, it's a piece of a shattered planet, a shard that somehow retained trapped gas to propel itself. Each of these ideas is brilliant from a physics standpoint, like mind-bending, but all of them depend on a series of extremely unlikely coincidences. The latest natural explanation, and maybe the most elegant, involves molecular hydrogen H2. Check this out. The idea is that cosmic rays, over millions of years, irradiated water ice in Oumuamua, breaking the H2O molecules and trapping hydrogen gas in the lattice of the ice. Then, as it passes close to the sun, the heat releases that trapped hydrogen. Hydrogen is super light, completely transparent, which explains why we don't see a coma, and if the release is uniform enough, it doesn't cause a spin-up. Boom. That's it. That's the outgassing explanation that actually addresses the big three: acceleration, lack of coma, and no spin-up. Elegant, physics-based, and natural. But even that doesn't completely shut the door on the alien tech theory. Because here's the thing: simplicity, man. In science, we like the explanation with the fewest assumptions. The natural hypothesis requires a really specific sequence: water ice heavily irradiated by cosmic rays, molecular hydrogen trapped inside, perfectly uniform release of gas, and a bizarre, extreme shape. That's a lot of moving parts, even if it's all physics we understand. Then you have the artificial hypothesis. Basically, someone says, maybe it's a light sail built by an extraterrestrial civilization. One assumption, one massive assumption: aliens exist and built this thing to travel between stars. But once you make that leap, suddenly all the observed data just fits. The acceleration? Perfect. No spin-up? Check. The shape? Perfect for a light sail. The non-gravitational push? Makes total sense. It's almost disturbingly simple. This is the core tension in the whole Oumuamua debate. On one side, you have conservative astrophysics saying, stick to known physics, stick to natural explanations. On the other side, you have this jaw-dropping possibility: technology from another civilization. And both sides are looking at the same data, but interpreting it completely differently. And honestly, I personally lean toward the natural explanation. The H2 outgassing theory is solid. It uses known chemistry and physics, and it's believable. But I can't ignore the alien theory entirely, man. That shape, a 10-to-1 aspect ratio, that's perfect for catching sunlight, like a solar sail. And the fact that it's tumbling, dark, uniform, all of it is just screaming at you to consider the unthinkable. Then there's the question of the trigger. What's causing the push? Is it a natural process, a silent, slow release of trapped hydrogen gas, basically a cosmic burp from a chunk of ice? Or is it deliberate, an intelligent design, sunlight pushing on a thin, metallic membrane, something built by aliens who might be long gone, or maybe still out there? That's the philosophical side of it, not just physics, but the question of intent. The public loves the alien possibility. Everyone on the media, everyone talking about it online, the Joe Rogan crowd, the artificial hypothesis is sexy. It's thrilling. But as a scientist, you can't let the story drive your conclusions. You follow the data. And the data, while ambiguous, still favors exotic natural explanations slightly more than tech. But let me tell you, even proving the artificial hypothesis is really tough. If Oumuamua were a probe, we'd expect it to be reflective, maybe shiny, maybe with some structure you could detect. Panels, seams, damage, something that tells us it's man-made or alien-made. But nope, dark, uniform, tumbling, just like any interstellar ice rock. The acceleration follows the sun perfectly, no course correction, no artificial maneuvers. It's passive. That's a huge constraint. And here's the Bayesian part, the part that makes your brain hurt if you think about it too long. Probability. Prior belief. We know interstellar objects exist 100% sure now. We've seen two, Oumuamua and Borisov. So any natural explanation starts with a high prior probability, but the idea of alien tech, super low prior probability. Even if it explains the data simply, the fact that the prior belief is basically zero keeps natural explanations in play. That's why astrophysicists are cautious. You can't just say aliens did it because it's simpler. You have to weigh what's actually plausible. And man, the whole episode of Oumuamua is a perfect example of science on the edge. We're inventing new physics, new chemistry, new formation models to explain a single, fleeting observation. We're pushed to the boundary of what's considered natural, and what we've learned is massive. It's not just about Oumuamua itself, it's about the sheer number of interstellar visitors that must exist. Based on the short window when we detected it, models suggest thousands of these things are passing through the solar system at any given time, 10,000 inside Neptune's orbit alone. We just couldn't see them before Pan-STARRS came online. So, Oumuamua isn't unique. It's the first one we've seen. And it could be a probe or a chunk of exotic ice. Either scenario is revolutionary. If it's a probe, the galaxy is full of alien space junk. If it's N2 ice, the galaxy is full of exo-Pluto fragments. Both are crazy, mind-blowing revelations. Then came Borisov in 2019, right? Borisov was much more normal. Comet with coma, tail, standard non-gravitational acceleration from water ice sublimation. It was the cosmic equivalent of a sigh of relief. Confirmed that interstellar objects are usually normal icy bodies. But that also made Oumuamua stand out even more. It's the control versus the anomaly. Now the field of interstellar object astronomy is exploding. We're building telescopes and survey strategies to find these visitors. The Vera Rubin Observatory is coming online soon. It's going to detect dozens, maybe hundreds, of interstellar objects in the coming years. And when we see the next Oumuamua-like object elongated, no coma, showing non-gravitational acceleration, we'll be ready. Maybe even send a probe to intercept it, finally answer the questions we've been obsessing over. I keep thinking about the moment it was discovered. That was pure scientific wonder. A messenger from a star system millions of years away, tumbling silently, dark, mysterious. It forced us to confront our ignorance and ask the biggest question of all: are we alone? And right now, the answer is hidden in that tiny, ghostly acceleration of a cosmic needle. Is it exotic, natural physics, or some alien tech? That is where the thrill is. That is where science becomes pure adventure. That's why we study this stuff. Because the universe just reached out and touched us with something completely unknowable. And man, it's beautiful.